Germany, 1939. In a secret bunker on the German-Polish border, Nazi agents were overseeing the production of a recently discovered chemical they'd codenamed Substance N. It boiled when they exposed it to air, it exploded when it touched water, it was lethal when inhaled, and when it decomposed, it spit out deadly hydrofluoric acid. When loaded into a flamethrower and ignited, it could burn at temperatures over 2,400 degrees Celsius. The plan was to arm troops with Substance N and use it to melt Allied bunkers into hot porridge. But then after studying it for a while, even the German soldiers were like, whoa. Experiments with Substance N were discontinued because the Nazis decided it was too dangerous to work with. Should give you some kind of sense of what we're dealing with here when we talk about the most dangerous chemicals in the world. I'm talking about things that explode when you touch them. Things so poisonous that if even a millionth of a gram went up your nose, it would end up killing you. Things that could even disable you because of their totally debilitatingly horrifying smell. And yes, chemicals so severe that even the Nazis thought they were crazy. Let's start with what the Germans had in that secret weapons bunker. They originally planned to produce 90 tons of the stuff every month, but only made about 30 tons throughout the whole war. What they'd concocted was chlorine trifluoride, the most vigorous fluorinating agent known to humanity. Fluorinating agents rip other molecules apart to replace their hydrogen atoms with fluorine. The result is what chemists call a violently exothermic reaction, in this case known as a fluorine fire. It's much more dangerous to handle than even fluorine gas, which, as anyone with a degree in chemistry could tell you, is not a sentence that you get to say very often. It's also a better oxidizer than oxygen. Oxidizers are compounds that steal electrons from other chemicals in a reaction, and they are what make combustion possible. Chlorine trifluoride is so good at this that it can burn stuff that sane people might think of as non-flammable, like bricks or asbestos, or things that have already been burned. Oxidizers are also used to ignite rocket fuel, and in the very short time that US rocket scientists thought about using this stuff as a propellant, they quickly learned that this idea was bad. In the early 1950s, the first time that US scientists tried to ship chlorine trifluoride in bulk, the steel tank cracked and a full ton of it spilled out. It burned so hot that the chemical ate through an entire concrete floor, and then a meter of dirt and gravel beneath that. One eyewitness described the spill only by saying, "The concrete was on fire." Chlorine trifluoride is still manufactured and is used by semiconductor companies to clean their equipment to within an inch of its life. The good news is that you can store it safely in a regular steel drum, as long as it's airtight and you're really, really careful, because it instantly scorches the inside lining of the container, leaving behind a non-reactive plating of metallic fluoride. Non-reactive is not a word that we're going to need when discussing the next chemical on our list, azide, the most explosive chemical compound ever created. This twitchy little compound is part of a class of chemicals known as high nitrogen energetic materials, and it does what it does because nitrogen just wants to be left alone. A nitrogen atom bonded with another nitrogen atom is one of the most stable molecules on Earth. Their electrons form an extremely strong triple bond with each other, which in nature can usually only be broken by a molecule being hit by lightning. The strength of that bond means that when two nitrogen atoms snap together, they release a tremendous amount of energy. So if you look at a molecule of AA, we're going to call it AA because azide is hard, you can see how it gets its bang. It has 14 nitrogen atoms, and because of the way the molecule is structured, none of them are in a triple bond. Instead, they're stuck in a loosely bound high energy state and are dying to move to a more stable lower energy state, which means releasing a lot of pent-up energy in the process. As a result, AA is both highly reactive and hecka explosive. How sensitive is this stuff? Well, it's actually hard to say because it's too sensitive even to measure how sensitive it is. A team of German chemists created it in 2010 with the help of the US Army in an effort to develop more energetic compounds. And their first report on the discovery, they said, and I quote, "The sensitivity of C2N14 is beyond our capabilities of measurement. Even the smallest possible loadings in shock and friction tests led to explosive decomposition." To give you a list of how touchy this stuff is, here's a list of things that make azide explode. Moving it, touching it, dispersing it in solution, leaving it undisturbed on a glass plate, exposing it to bright light, exposing it to X-rays, putting it in a spectrometer, turning on the spectrometer, and my favorite, absolutely nothing. They had it in a shock-proof explosive case in a dark climate-controlled room, and it blew up. I think somebody said something mean about it somewhere, and it was like, The lead scientists on the team that synthesized it called it a very exciting discovery. If I worked with azidoazide, waking up every morning and seeing that I still had all my fingers would be a very exciting discovery. Next up, let's talk about dimethylcadmium. This is an organometallic compound, which means that it has a molecule in which carbon has bonded with a metal. In this case, that metal is cadmium, a pretty nasty customer all on its own. So far, we've talked about chemicals that explode or cover everything in unquenchable fire, and don't get me wrong, dimethylcadmium, it does that too, but that is not what makes it so dangerous. It is, in all likelihood, gram for gram, the most toxic chemical in the world. It has both acute and chronic effects, which means that it will kill you now and later. It was first prepared by a pioneer of metal organic chemistry, a fellow named Erich Krauss, who was from, yes, Germany. It was 1917. To give you a sense of how Krauss rolled, he died in his lab at the age of 37 after accidentally inhaling a bunch of chlorine, but before that happened, he managed to report his discovery of dimethylcadmium. When you breathe it in, it is absorbed instantly into your bloodstream, where it basically serves as a kind of chemical chauffeur for toxic compounds of cadmium to travel all around your body. Because it's so effective at exploiting your bloodstream, it quickly affects your most blood-infused organs, like lungs and your kidneys and liver, creating compounds that rip electrons off the atoms of your cells. But if you manage to survive your first few hours after dimethylcadmium exposure, don't get your hopes up. It's also extremely carcinogenic, so it will take you down with cancer just to spite you. This stuff is so potent that as an airborne vapor, just a few millionths of a gram per cubic meter of air meets the legal safety limits. But if you spill it, how are you gonna clean it up? Water? Well, when it reacts with water, it produces both lots of heat and lots of hydrogen gas, which is flammable, so yeah, it explodes in water. Maybe you could sweep it up? Friction makes it ignite. Might want to just try waiting for it to decompose? Well, it will do that. It'll form a crust of dimethylcadmium peroxide, which is a friction-sensitive explosive, so you're just one shoe scuff away from kablamo. And on top of it all, the chemical has an odor that's been described as foul, unpleasant, metallic, and disagreeable. But that's nothing compared to our next chemical, thioacetone. It won't explode, or start fires, or even give you cancer. Compared to other chemicals on the list, it's like a cute little fluffy bunny. If that cute little fluffy bunny had the most ungodly stink you can imagine. That's right, thioacetone takes the prize for the world's smelliest chemical. It's a thiol, an organic compound in which a carbon atom is bonded to a sulfur-hydrogen pair. They're all gross. A skunk spray uses 2 different thiols to eye-watering effect. Most sulfur-containing compounds are released by rotting meat, which is a reason why we would want to be very good at being able to detect them and also not think that it smells good. But when it comes to bad smells, thioacetone takes the stinky, seriously unappetizing cake. You can smell 1 drop of this substance almost instantly from half a kilometer away. In the 1960s, a vial of the stuff fell off a shelf in a research lab. People were chucking their cookies in buildings 200 meters away. But the greatest example of thioacetone's silent but deadly strength comes from the German city of Freiburg, where in 1889, chemists at a soap factory were reportedly working on a larger molecule known as trithioacetone, which is used as a flavoring and a fragrance. But when they broke it apart into thioacetone, workers started falling ill. Spontaneous outbreaks of vomiting were reported in the surrounding neighborhoods. It led to the evacuation of the whole city. There might be a lot to learn about thioacetone and thiols in general, but understandably, scientists are not really rushing to look into it. And finally, there's the strongest corrosive agent in the world, the most dangerous acid ever devised by humanity, fluoroantimonic acid. Because what list of dangerous chemicals would be complete without a superacid? What makes an acid is its ability to donate a proton to another molecule nearby it. And a proton is just a hydrogen atom that's lost its electron. This process is called protonation, and an acid's strength is determined by how willing it is to give up that proton. A weak acid, acetic acid for example, which is just the undiluted form of vinegar, will drag its feet about protonating other molecules. Most of it will just sit there doing nothing. But a strong acid, like sulfuric acid, will punch that proton in the air like a beach volleyball at spring break. And remember from Substance N how crazy fluorine is? Well, fluoroantimonic acid is 10 quadrillion times stronger than sulfuric acid. This molecule is begging for an excuse to fly apart. Once it's lost its hydrogen atoms, the remaining atoms of fluorine and another element, antimony, tear through everything else around them, from ripping electrons off nearby molecules and leaving just organic goo in their wake. Especially exciting is that fluorine really likes to bond with calcium, so once the acid tears through the fatty organic tissues of your skin and muscles, the fluorine will burn through your bones. The only way to store fluoroantimonic acid is in Teflon containers. Teflon, by the way, is held together by carbon-fluorine bonds, which are the single strongest bond in organic chemistry. We don't actually know a lot about this acid because it's so hard to do experiments with it. You can't put it in a syringe or on a slide. It eats through glass like it's cotton candy. You can't put it under a fume hood. It'll eat the fume hood. All you can really do is just look at it, ideally from very far away. Thank you for watching this particularly dangerous SciShow infusion. Thank you especially to our Subbable subscribers who help us make this show for them and for everyone else. To find out how you can support us, you can go to Subbable.com. And if you want to keep getting smarter with us, you can just go to YouTube.com/SciShow and subscribe.